So we will continue with our discussion on errors today. I hope to finish the topic today. There might be some spillover for next Tuesday, but we should cover most of the material on errors today. Your homework one is due today at midnight, so go ahead and submit that. I see some still requesting Jupyter Notebook access on CHPC, so I hope that's gonna be working for you. Some of you have had issues with PDF submissions. We're working through that offline. Hopefully by homework 2, there are no more of those issues anymore. I want to remind you where we left off last time, where we were doing this example by hand in class. And to recall, we were looking at the relative approximate error. We said that in practice, you can't measure a true error. You can only approximate what the error is, the error that you're committing in a numerical calculation. The great part of that is that you can base that approximation of the error only on the approximations that you're using, okay? So a higher order approximation minus a low order one over the high order one, or if you're doing an iterative procedure, the current approximation minus the previous one over the current one, right? So all you have to do is use the values that you are working with, okay? And we went ahead and did this example. I asked you to use the Taylor series to evaluate the exponential function using 1, 2, 3, and 4 terms and report the relative approximate error for each term. So clearly what this is saying is that the exponential function can be approximated with this polynomial, but we can't use an infinite number of terms, so we're going to employ a finite number of terms. We will, in a few minutes, call this a truncation procedure. If you do 1 term or 2 terms or 3 terms or 4 terms, you're committing an error. The more terms you add, the less that error is going to become. And you were asked to do this calculation, so we went ahead and did that. We kind of rushed it at the end of class. We're not going to do that here right now. We're going to do it in Python, but you should work through this example at home, okay? These are examples of what you will have to do in an exam, okay? But if you look at the number of terms and how the error changing, this is the relative approximate error. Clearly, we are reducing the error as we add more terms, okay? That's the beauty of this procedure. Now, you might ask, okay, so this is kind of like, I know what e to the x is, and you know, these functions, like how can we use this concept of approximate error in practice? It is quite useful, okay? And this is a specific example of that, is that you could say, I want to keep adding terms in the Taylor series for a function. Let's say you want to evaluate sine 3.5 or exponential 0.73. When do you stop adding terms? Do you add 100 terms, 1,000 terms, 5 terms? How do you know when to stop, right? Oh, okay, Connor has, go ahead.
I was going to say depends on how exact you need to be in geometry.
Okay, so how exact you want to be in your approximation. And we're going to measure that. So what your colleague said is the number of terms you need to add is going to be dependent on how good of an approximation you want for the function, in this case, the exponential. Okay, so if we are able to track the approximate error as we are adding terms, we can say, oh, we want to stop at an approximate error of 1% or 5%. Okay, and then the code will automatically keep adding terms until you reach that threshold. You will see with this Taylor series example is that for different values of x, to achieve a certain error, you're going to need different terms. So if you're doing e exponential 0.1, you might get that in 2 terms. But if you're doing exponential of 100, okay, you might need 200 terms to achieve the same error, okay? We call that tolerance, all right? So here's your coding activity. You are going to write a Python code that implements the Taylor series to evaluate the exponential function, okay, down to an error or a tolerance of 1%. Okay, so you are to implement this Taylor series. You're going to keep adding terms, however many terms we need, until you keep adding terms until the error is less than or equal to 1%. At what value of x? Doesn't matter. We're going to try it for different values of x. Okay? So get your Jupyter notebooks up and running, and let's try to do that together, okay? So like last time, we learned a lot of stuff with Python. We learned indexing and slicing through NumPy arrays. Today, we're going to be learning an important feature, which is for and while loops, specifically while loops, okay, which are very powerful, okay? So go ahead and open up a Jupyter notebook, start working. If you don't know where to start, try to think about where you want to start, okay? Try at least just to think about it. That's as important as writing the code itself, okay? Again, when faced with a programming question, ask yourself, what do I need to supply the code? What is the code trying to give me? What to do? What is the code going to do? I need to add terms in a Taylor series. So that's not complicated. Like, how do you do that? You could do it with a for loop. You could do it with a while loop, right? If you do it with a for loop, you have to specify the number of terms, right? So how many terms do you set? With a while loop, it's probably going to be a little bit better. So go ahead and give it a shot. Spend 5 minutes on this. Work in groups, please. Okay, work in groups. I want to hear you buzzing. You're allowed to talk now. You're allowed to be very loud.
Differential equations like 2 years ago.
Hey, I'll be able to help if you want to. It looks like you're doing the two-way wave equation. Yeah. Hey, McKenna. Glad you were able to make it back. Okay, let's see. I'm walking around. Use me. Call on me. You should try to figure it out. You can look at the code, but you're not going to learn anything. So I have the answer online. All the notebooks are online. You can get them. It's not me. Yeah, go ahead.
What is the equation for relative approximate error?
Okay, the equation for relative approximate error, good point. I'll copy that, put it up here. It's the current approximation minus previous approximation over current approximation, okay? So let me remind you of that. Okay. Hey, Brooke, thank you. You guys made it. Hey, Brandon.
So I think we're all a little confused. Are we starting up here with the first question marks?
So you're working through the Jupyter notebook with gaps? No, we're not starting there. Yeah.
Oh, there's two.
Yeah, you don't have to. Yeah, you can use that if you want. There's some inspiration there, but I'm gonna do this from scratch. So if you want to look at the notebook with gaps, it's the last part.
Oh, okay.
Yeah, it's the last part.
This one?
Yeah, but typically, I'd like you to try to do it without looking at this.
Oh, so this
Yeah,
is the answer.
exactly. Yeah. No, I didn't end up using the notebook with gaps. I know I told you to download them last time, but I did things differently this year. Yeah. Okay. Yeah.
Is this supposed to be for all x, or is there a specific value?
Does it matter?
It doesn't matter.
It shouldn't matter, right? You're programming. Does it matter? Does the Taylor series tell you anything about x here? Doesn't.
No, it doesn't.
Yeah. So you should be able to provide any value of x and continue calculating. Yeah.
I can choose a value and have it, because it can't do this. This can't do algebra.
This can do what?
Python can't do algebra, right? So if I put like a function divided by another function, I need to find x, it's not going to. Does that make sense?
X is a value supplied to your routine. So you can use that value. There's no algebraic functions. There's no symbolics here. Okay? So any value of X, you just keep adding terms, okay? Just keep adding terms. Okay. You got it. Okay. So how we feeling? Bad Python, bad, difficult Python, or like, yeah. This is really like, after today's lecture, this is pretty much what you mostly need for the most part to work through the course, okay? So, should I open up my notebook and start working on this together? Yeah? Okay, let's do that. All right. Let me see. Okay. All right, so let's start a new notebook. Okay, let's zoom that in a little bit. Okay, let's import our boilerplate. Okay, we're finishing it up. Okay, for those who want to focus with me. Okay, so let's import the boilerplate. Import numpy as MP. That's all we're going to need. Okay, so first what I want to do is attempt to write down the Taylor series with a fixed number of terms, right? Say I want to create the exponential Taylor series just with 10 terms or 18 terms or 20 terms, okay? Because I want to teach you a little bit about the for loop, but also show you the limitations of the for loop, okay? So we're going to start by, say I'm like, okay, I don't even know where to start. I'm just going to start by writing x equal 2. Let's say I want to evaluate exponential 2, okay? Suppose you want to evaluate exp to the 2, okay? E to the 2. Okay. Now for my Taylor series, because it's a summation, I'm adding terms. I need a container. I need a bucket, a place to put all of those terms. Okay? Start with the first term and then add the second term, add the third term. Agreed? So I need a variable that is going to contain that summation. Now because we're adding things, I'm going to initialize that variable to 0 because 0 plus something is that something, right? So I'm going to create my bucket. I'm going to call it result. Because it's kind of very significant, the word result. This is my result, right? So I'm going to create result and call it 0, set it to 0.0. That's where we will store bucket to store Taylor series terms. Okay? Perfect. Now we said we want to, let me open up my slides again. We said we want to do a tolerance up to 1%. Which is, 1 over 100, right? That's my tolerance, okay? That's the tolerance. We want to check if we are at that tolerance. Yes, Emily?
Is there a reason why you put 0.0?
Yes, that's a great question. So Emily is saying, why are you putting 0.0 rather than 0 or 1.0 rather than 1? Because I do not trust Python all the time to treat all my numbers as floating point numbers. There's a risk that Python is going to treat a number as an integer, and then you'll end up doing integer arithmetic rather than doing floating point arithmetic. So you might end up with an occasion where you're dividing 1 over 3, and it's going to give you 0, because the integer division of 1 over 3 is 0, not 0.333, right? So to enforce the fact that, to tell Python, no, these are floating point numbers, you put 1.0 over 3 or 1.0 over 3.0. Once Python detects a decimal point, it automatically assumes that the number is a floating point. Great question. Thank you. Okay. So in this case, I didn't put 0.0 in the denominator because I have 1 in the numerator. But to be more careful and cautious, put a decimal point 0 everywhere. Okay? Okay. The simplest way to add these Taylor series is to just keep adding terms. Let's say we want to add some number of terms. We can do that with a for loop. So here's how I would write my pseudocode. I want to say, for something, okay, add terms to Taylor series. Okay, so let's start with the for loop first. In this case, we just need a counter. 1 term, 2 terms, 3 terms, 4 terms, 5 terms, etc. The simplest counter is one provided by default in Python. It's called a range, okay? And that automatically goes hand in hand with the for loop. So you will remember this forever. You would say for I in range. And now in the range function, that's a function in Python. Now notice how it automatically turned green because it's a built-in function in Python. Now what does range take? What does range take? If you forget, you put your cursor in the parentheses and press Shift-Tab. Beautiful. Shift-Tab gives you the documentation of any function. You put your cursor in the parentheses, gives you the documentation. If you press it another time, it expands that documentation even more. Now what this is telling me is that, how do I use this? If I use range stop or range start stop, it returns an object that produces a sequence of integers from the start, okay, inclusive, to stop, exclusive. Okay? So if I set a range from 1 to 10, it's going to give me numbers 1, 2, 3, 4, all the way to 9. You don't believe me? If you're in doubt, print it out. Yes. If you're in doubt, yeah, print it out. Let's print it out. So for I in range, let's say from 1 to 7, print I. It counted. It created a counter. Counters are important, apparently. So you need to count things. Let's try again. For I in range from 0 to 7, it's going to go 0 all the way to 6, right? Could we do a range with a negative number? Sure. Minus 5 to 7. Goes from minus 5, right? Could we step? Well, the doc string or the documentation tells me that, yeah, I have an option to step. So rather than go by increments of 1, I can do increments of 2 or increments of 3, right? So minus 5 to 7 with increments of 2. Look at that. Minus 5, minus 3, minus 1, 1, 3, 5. Okay? What if I put just a number, one number here? For I in range 7. It automatically starts from 0. Okay? Again, you memorize none of this. You print it out every time you forget it. But what is important here, like I said in the first lecture, is the thought. What do I need to get this summation? I need a counter. And I remember this range function. If you remember that one thing, range, then you can read the documentation. No need to occupy this disk space up here, with minutia like that, right? To me, these are like little details I don't care about. I never remember syntax, okay? I'd rather remember your names, like I said, okay? All right, so now that we know how to do a range, here's what we're going to do. We're going to provide a variable called number of terms in the Taylor series. And let's say 100, okay? These are number of terms in the Taylor series, okay? Now, I did not put a decimal point here because this is an integer, okay? And Python is going to treat it as an integer. If I had put a decimal point over here and put n terms in the range, it's going to throw an error because it cannot loop over a floating point number, okay? So this is the first step here. For I in range n terms, okay, this is the first step. If I print I, it's going to create 100 terms for me. Term 1, term 2, all the way to term 100. The index is 99, but it's 100 terms in total, okay? Well, that's great. Now I have a counter, okay, that I can leverage to do the Taylor series. Okay. Now with the Taylor series, my result is going to be, I need to add terms in the result. So let me bring up the slides here again, because it's a summation. Window, move to Creston, right? So I have a summation over here, 1 plus x, etc. So the formula is 1 over n factorial x to the power n, okay? That's what I want to add. That's what I want to create. And with the range, I'm going to keep adding more and more terms to the result, to my bucket, okay, to my bucket. All right, so we started with result equals 0, okay? Now I want to augment my result. I'm going to say, and if you haven't seen this before, this is like a big idea in programming. Here's what I'm going to write. I'm going to write result equal result plus 1 over math.factorial I times x to the power I. Just give me a moment here, and I'll explain. Import math. I need to import math because I need the factorial. Now you agree that, forget this first statement here, but you agree that this is 1 over n factorial, 1 over I factorial or n factorial times x to the power I. That's this formula, right? We agree. If I had written this summation in terms of I, summation going from I equals 0 to infinity, right? That would be that formula. We agree with that. Nobody is worried that that's, so we agree with that. Okay, great. What about this one here? Who doesn't like this? Who thinks that result equal result plus something? That's kind of like mathematical blasphemy, right? X equal x plus 1. That means 1 equals 0, right? No? Is there anything wrong with that? Do you think there's anything wrong with that statement? Plus equal, but that's the same thing. This is going to drive a point, though. Who thinks this is an issue? Do you think that's an issue? Yeah. Okay. And you wouldn't be wrong. When I first learned programming and I saw this statement, I was like, what are you talking about? This is like x equal x plus 1. That means 1 equals 0. That's wrong. And however, this is not mathematics. This is programming. What this is saying is that when you write a variable in any code, it's actually looking at memory. And on the left-hand side, what the code is saying, the new values in the memory, everything on the left-hand side is new values in this memory location. And on the right-hand side are equal old values and other things you want to add. So what this is saying, the new value of result is equal to the old value of result, the current state. So my new state is going to equal to the current state or the old values, whatever was in there in that bucket, plus that additional term. So what it does, it creates another temporary memory, moves the old value in it, and adds the thing, and then brings it back to the memory. This is not math. This is not equivalent to x equal x plus 1. Okay? You can do any operation. You can do this is equal result plus or minus or divided or multiplied by. It's the same thing. This is useful because I don't have to create 2 more variables to move old result, put it in a new result, and carry this as things around multiple buckets. I can just reuse my existing memory, okay? Well, this is it, really. By the time I'm done with n terms, if I print result, okay? Let's print result. It should give us a value. Look at that. Okay, so let's compare this to np.exp of what was x. That's pretty darn good, right? Now, if you do 5 terms, it's going to give you 7.0. If you do 6 terms, 7.2, etc. Okay. We just did a Taylor series. Yes?
How is the first value for the actual Taylor series that on hand it's going to be 1, but then for this first result,
It is going to be 1 for this first result. Because it's going to be 1 x to the 0, right? It will be 1. It will be 1. 1 over 0 factorial is 1 times x to the 0 is 1. It is 1. But if the formula does not result in the right thing, then you initialize your result with 1. And then you fix your indexing, okay? But this works for this case. Okay, so now let's calculate the relative error, okay? So we're after the relative approximate error, okay? Okay, so what are we going to do with that? If I type the error as, let's say, current approximation, I'm just going to type it minus old approximation, okay? And then over current approximation, right? That's the definition, over current, okay? What that tells me is that I'm unfortunately going to need another variable to store the old result, okay? Because I'm reusing here my result. I already updated it. I no longer have access to the old one, okay? I no longer have access to the old one. So what I'm going to do, I'm going to create a temporary variable and call it old result equal result, then update my result, and then finally I can do the error calculation, absolute value of old result minus result, okay, over result times 100, okay, and then print. Let's print something useful. Let's print something useful. Let's say we're going to print the number of terms we've added so far and print the error. Okay, and over here I'm going to do some formatting. I'm going to say the first column is number of terms, and then, and then error, percent error, okay? Okay, so this is what I got. Initially, it's got 100% error, which is fine, and then 66, 40, 21, like we did by hand, and then 9, and then 3, okay? That's for 6 terms. But we didn't reach our tolerance, because our tolerance was 1%, not 3.6%. So in this case, we need to add more terms. So you have to go and manually change the number of terms. But what if I change the value? Okay, so let's say for this guy, if we do 7 terms, or, okay, we reach an error of 1.2%, and then if we do 8 terms, then our error is 0.3%. Okay, good. Now let's change x. Let's say we want to evaluate this at x equal 20. With 8 terms, our error is 67%. So now we have to add more terms. Okay, so I'm going to go back and say, okay, let's do 20 terms. Okay, with 20 terms, we're still at 18%. Like, this is annoying. You might say, why don't you add 1,000 terms? Well, that doesn't guarantee a thing. What if I want to do exponential 2 million? I'm not going to reach that tolerance. And besides, if you can get the solution with 6 terms, you're wasting doing calculations for all the other 980 whatever terms, okay? So it's not efficient. It's not a good way of doing it. But you learned about the for loop and you learned about range. Okay, let's do it right this time. The other option would be, instead of adding terms, it's like we want a mechanism to keep adding terms until something happens. without an upper limit. Just keep adding terms to infinity until something happens. And that something is when the error becomes less than 1%. Turns out, the combination of a for loop and an if statement is called a while loop. Literally, like you would say it in English, you know, while there is a mess in your room, my son, you are not going to get dinner. Okay? So as long as there's a mess in the room, there's no dinner tonight. Okay? Exactly the same. We're going to say while the error is greater than 1%, keep adding terms. Once the error is less than 1%, or whatever tolerance you said, then we're going to stop. Okay? So let's do that. So that's going to be our formal solution to this problem. If I can find my cursor. Okay. All right. Let's do it now with a for loop. Okay, we don't need this anymore. We don't need this anymore. No, we're not going to do a for loop. We're going to do a while loop now. Because we're going to combine the for loop and an if statement or a while loop. They become a while loop, okay? Yep. So I'm going to start by setting my error. I'm going to call it error. I'm going to put it a very large number, 1 million. And I'm going to say while my error is greater than my tolerance, which we defined earlier. Let's redefine it here. Tolerance is equal to 1 over 100. Okay? While my error is greater than my tolerance, as long as the error I'm committing is greater than the tolerance, keep adding terms. So here's what we're going to do. We're going to copy and paste these guys here because they're going to be the same. Okay? Old result is equal to result, and then, so we need clearly a result variable equals 0.0. Okay? However, when we go to a while loop, we lose our counter. Right? We don't have an I anymore. This is still correct, but I don't have an I. So if I run this, it's going to crash. What is I? I don't know what I is. And I need to keep augmenting I every time I visit the while loop. The answer is simple. Solution is simple. You create your own counter. You'll initialize I equals 0 over here. And you enter the loop. Think of it this way. Python enters this loop, looks at error. My initial value of error is 1 million. It's definitely greater than 1%. Okay? So it's going to go inside the while loop. It goes here, creates a new variable called orResult, copies the value of result, and then updates result. Okay? Goes in, I is equal 0 over here. Great. Okay? Calculates an error. Now the error over here, let's call it error. So it updates the error. And then internally, Python says, automatically checks for, okay, so it's done here, calculates an error. It goes back here and says, my error now, is it greater than tolerance? If yes, do this again. All we need to do is update this I. So here's what we're going to do. We're just going to augment it by 1. Every time we visit the while loop, we're going to augment our counter by 1. Because that's the summation in the Taylor series. 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, right? So all we have to do is say I equal I plus 1. All right, so now in the end, I'm going to print final error is equal to my error, and print number of terms to achieve this error, number of terms needed was equal to I. Okay? All right, so I'm going to do my x value equal 2 over here. Okay, so it needed 11 terms to reach a tolerance of 1% to compute E squared. Okay? Now let's change your the x, let's put 20. With 20, it needed 40 terms to achieve that tolerance. Minus 3. It needed 17 terms. It's not bad. Go back to the recording and go step by step and change things around, play with the code, change numbers, ask questions about it. So once you know these things, for loop, while loop, indexing from last lecture, we've pretty much covered 80% of what we need in this course, 75%. Okay? Yes. Yeah, you need to put comma and put I, or I minus 1, or I, it doesn't matter. Yeah. The code is in the lecture notes, and it's in the recording, okay? All right, we have about 20 minutes left. Let's continue with the lecture. Move to built-in retina display. Okay, so this is a summary slide of the errors we defined. In those, we spent 3 hours on talking about just about errors. Okay, so this was important. All right, so now we had some definitions. We have a sense of how to calculate numerical errors. Next, we're going to talk about the sources of these errors. We have a vague understanding of where these errors come from, like round-off or truncation, but we're going to solidify those ideas now in the next few slides. Okay? In general, in any engineering system, you have a hierarchy of errors. The first error we commit is a modeling error, is our perception of nature. How fluids flow, we have a model for that called the Navier-Stokes equations. It's a model. It's pretty darn good and accurate, but it's just a model. The equations of relativity are just a model of reality. Even quantum mechanics, regardless of how accurate it is, it's still a model, a perception of what we observe in reality. Okay? Clearly, there are good models that are better than other ones for different systems and different situations. But that's kind of the first top level of errors that you encounter. We are not dealing with that in this class. You'll deal with that as you become, a senior, as you reach your last few years of classes, okay? Last few classes. Then there are programming errors, like you have a mistake in your code instead of looping over n or n plus 1, or you did the wrong conversion between variables. This is a programming error. It's not a numerical error. We kind of encounter that here, but strictly that's not a numerical error because it's a human-induced error. It's not something, it's something you have control over in a way, okay? And then finally, there are numerical errors, which is our main concern over here. There are generally two types of errors, really just two types I've seen in my life. Roundoff errors, which we've seen the ominous example of with the Ariane 5 rocket, okay, where every time you put numbers on a computer, you have roundoff. Every time you add them, multiply them, divide them, subtract them, do any operations with numbers on a computer, you have roundoff. No questions asked. The higher precision you use, the better, but you still have roundoff, okay? Then there are truncation errors. Truncation errors are also part of the numerical approximation process. You will see that the foundation of all sorts of simulations that we do, all sorts of curve approximations, is going to be the Taylor series, the one we just computed. And just like we did, we computed only 5 terms or 6 terms or 7 terms. Everything that we left off is truncation error. Because we took an exact mathematical expression and truncated it up to a desired number of terms. How we choose that number of terms is a different question. But everything that we left off, that's an error that exists compared to what we think the truth is, okay? So 2 errors in numerical methods are round-off errors and truncation errors. There's the third type, iteration error. I'm not going to talk about this because we're not going to cover iterative methods. That only shows up in iterative linear systems, so I'm going to delete that from the slide, so don't worry about that. Round-off and truncation is what we're dealing with. All right. We start with round-off, and I'm going to give a very rudimentary overview. We're not going to get into binary representation of numbers and all of those things. That's not a concern to us. But you have to understand, to a certain extent, how computers represent numbers. Okay? So typically, computers represent numbers up to a finite precision because there's a finite number of slots in memory to represent a number. Because computers are digital, they have to use binary, 0 or 1. It's a state of a semiconductor in the memory. It's either charged or discharged. And based on that state, we can represent a number. It's a brilliant idea when digital computers were first created. Okay? Now, roughly, this is not how it is, but roughly the way to think about it is that each digit in a number occupies a bin in memory in the computer. Okay? It's first converted to binary, and the binary numbers occupy the bin. But that's how it's represented. But typically, you have a limited number of bins in memory. That's when you hear, oh, this is a 16-bit computer or 32-bit. I existed on this planet. My first computer was an 8-bit computer. Okay, the hard drive I had was like 100 megabytes, was this big, like this big. I still have it. Amazing where you know how far we came. Now we have computers with 256 bits. So these bits are slots in memory, physical slots that can contain binary numbers, 0 or 1, to represent an actual number. Okay? So roughly, this is how we represent numbers. Now, in reality, when there are less bits than there are numbers, then when there are less bins than the number can represent, so for example, you take that number and we can only represent these first digits, 0, 1, 5, 4, and 6, then everything else is erased. It's either rounded up or just chopped, okay? So you lose some of that precision in your number representation. Now, the worst issue with round-off numbers is when you combine low precision with high precision numbers, and you commit that error that the Ariane 5 rocket committed, okay? But if you're only working with 24-bit or 16-bit, and you know the limitations of what you can calculate, then you know that's the world you live in, and you're fine, okay? That's fine. That's a non-issue. Yes?
In this case, would this be a 5-bit representation?
No, because I didn't do the binary. But yeah, for the purposes of this discussion, it's a limited representation of that number. Because this number is first converted to a binary representation, and then the binary is stored in memory. Yeah, each one is a bit. Yeah, so this could be actually a 12-bit number in an actual binary. Okay, so, but the point is to illustrate the concept here. So formally, the round-off error is the result of the inability of computers to represent all significant figures in a number. It is therefore the difference between the actual value of a number and its rounded representation on the computer. Okay? The more bits you have, the more significant figures you can represent. So you hear things like this is a 16-bit float, or 32-bit float, or 64-bit float, you know, single precision, double precision. This is oftentimes called half precision. Okay, and 128-bit floats. Now, the more the higher the bit number, the more memory a number is going to occupy, right? So you can say, oh yeah, let's do our simulations all at 128 bits. Suddenly, you're doing a 3-dimensional simulation with 100 million variables, And you don't have enough memory to store those variables, right? Well, memory is cheap now. We can buy. Then you have issues with moving data around. In our COVID study, we did the analysis in about 2 weeks, but the simulations, but the data analysis took 4 weeks. To render one movie, just one simulation, one animation, it took about 3 days of continuous crunching. Yeah. And that was like using like standard 32-bit precision, okay? So in reality, this is what it is. It converts a number into a binary, and then the binary are represented here in the digits. You don't need to know that, okay? I do have an example for you to try at home if you want. And we're not going to do it in class in the interest of time, but you can work through that at home if you want. I have the code on the next slide. But you can use Python to mimic 16-bit, 32-bit, 128-bit numbers, okay? You just have to declare them appropriately. So, for example, here I can create a number with 16-bit precision, or 32-bit, 64, or 128. You can use this function call to create that number. The question here is take the number 10 to the minus 5 and add it to itself 100,000 times. The result should be equal to 1 exactly. However, when you run it, with 16 bits, you get an error of almost 0.1 between, so your answer is almost 0.9. You imagine that it's not 1. And that's with 16. So imagine you're adding it even more and more. You're going to drift from reality, okay? So that tells you that when you have a lot of repeated calculations, round-off errors can add up and can become significant, okay? Okay, here's another unfortunately ominous example. There are no happy examples with round-off errors. It's pretty much every example you see. There was a stock market crash in Canada. There was an oil rig that collapsed in Sweden. This is another example that actually cost a lot of lives. None of the other ones cost lives except this one's of the ones I know. What I'm showing here is a system developed by Raytheon. This is a defense contractor in the U.S. So they make, military devices for the military. In the 90s, during the Gulf War, etc., the U.S. had a few bases in the Middle East, and one of them was in Dhahran in Saudi Arabia. And they had implemented the Patriot missile. This is like one of the most popular air defenses that was created in the world, okay? Like Israel right now have what they call the Iron Curtain. So essentially it tracks any missiles flying, coming to kill you, and it shoots them down, okay? So automatically, it's like constantly scanning the sky. If it's a bird, it needs to know that it's a bird, not shoot it down with like a $100,000 missile, right? But if it's a missile, if it's a rocket that's coming to hit you, it tries to shoot it down, okay? It's a pretty advanced defense system. The way it works is it's got a few radars, and it's constantly scanning the sky. And then, just like a radar, you see all those green radars in the movies, like beep, beep, it detects something. Okay, so the first sends a pulse, and the pulse comes back, so that gives you the distance, the difference between the timing and the pulse, just like when you're speeding on the freeway. Of course, none of you speed on the freeway, but when you're speeding on the freeway and the police officer has a radar kind of straight shooting at you, so it sends a signal, the signal bounces back. The time difference between those two signals, okay, can tell you how far you are. Right? Because we know the speed of the signal is 300 kilometers per second, 300,000 kilometers per second. Okay, that's the speed of light, an electromagnetic signal. So we measure the difference. We sent it at 20. After half a second, it came back, so we know how far the object is. Okay, then we do another one. We can measure the speed of the object. Okay, so this is the same thing with the Patriot missile. Detects an object, knows how far it is, then shoots another signal. It identifies the speed, and then apparently it passes this information. Then it knows like, oh, I might have a rocket coming over here. And then it keeps tracking it. And then apparently there was one last radar, okay, that shot a signal with a 48-bit timer and then the signal returned back and was registered with a 24-bit precision timer that was running for about 100 hours, and it accumulated an error of 0.3 seconds. But with this, when in reality what happened in 1991, a Scud missile from the Iraqi military was shooting at the US barracks, and that Scud flies at like 1,700 meters per second. So this is like a hypersonic rocket, okay? And because of that slight error, it thought it was like a bird or something, and it didn't shoot it down, and the Scud missile destroyed the barracks and killed a lot of people. There was a huge investigation about it. So this is a story on Wikipedia. February 25, 1991, an Iraqi Scud missile hit the barracks in Dhahran, Saudi Arabia, killing 28 soldiers from the US Army's 14th Quartermaster Detachment, okay? And then the government investigation showed that there was a software error in the system handling of timestamps. The Patriot missile battery had been in operation for 100 hours, by which time the system's internal clock had drifted by 1/3 of a second because it was using a 24-bit register. It was committing an error. In homework 2, you are going to solve this problem, okay, by hand, okay? And you'll crunch those numbers and you'll see how big of an error roundoff can be, okay? Anyway, you can read the article. There's a lot of YouTube discussions about it. Some other stories, there's a website that tracks roundoff error stories. So the Ariane 5 I showed at the beginning of this lecture series, Vancouver Stock Exchange, it chopped stock tracking index to 3 decimal points, producing a loss of 500 points in the index. That's like a big deal. If you are an index investor, you put your money in the market. You don't know how to invest, you just buy the entire stock market and let's track things. So apparently the stock exchange was like, you know what, we don't need to worry about those few higher decimal points, right? If you had $1 in the stock market, that's not a big deal. But if you had like $100,000 and you chop it to 3 decimal points, you're losing thousands of dollars in that. And so it caused like a huge crash. Anyway, now, should you worry? No, don't worry. I want you to use, don't go burn your computers now and say, evil. No, computers are good. They're still useful and helpful. And in practice, most engineering and mathematical systems will cancel out any sort of errors that you accumulate, okay? Modern computers have, the default precision is 32-bit at least. And as we move forward, it's going to be 64-bit. It's going to hide any round-off mistakes that you commit, okay? So you should not worry about that. However, don't blindly just trust numbers just because a computer gave them to you, okay? Don't just trust them because a computer gave them to you. Pay attention. Make sure things are consistent, okay? This will be harder when you're dealing with very large codes, okay? Like my code probably has a few million lines of code in it and has the fingerprints of dozens of students and people. And I can't keep track of all of that. And so, we keep our fingers crossed. Every now and then we observe some anomaly, okay? And we're like investigators. Thankfully, nothing has to do with round-off errors. But sometimes there are errors committed, and instead of assuming a float, the student would assume an integer, would hard-code it. But then we see that in their results. So this result doesn't make sense. Let's look at your code and okay, that's your mistake there, okay? So, don't worry, but be vigilant. All right. Next, I'm going to talk about truncation error. Truncation error, so in homework 2, you're going to solve the Patriot missile problem, okay? It's an interesting problem, and you're going to have a lot of questions of how to do the calculation. We'll be there to help you out, but you'll be able to get exactly, understand the issue that happened exactly with that situation. Okay. Truncation error, like we said, is the result of truncating an exact mathematical expression and only taking a portion of that. Whatever you leave off that full exact mathematical expression is the truncation error, okay? An example is the truncated Taylor series that we just dealt with when we only used 5 terms or 6 terms or 100 terms. All the other terms that we didn't touch are the truncation error. Now, I'm going to use this opportunity to actually introduce you to the Taylor series or reintroduce you to the Taylor series. I'm just curious, who studied Taylor series in high school or in 1703? Okay, just a point of hands. Okay. Okay, so we're gonna reintroduce them again with a different perspective. We're gonna revisit them later. We're gonna even spend more time on them a little later. But the idea of the Taylor series, it's used in many different contexts. But the fundamental idea is that if you know the value of a function at a given point and know all the derivatives also at that point, so the rate of change, the second derivative, third derivative, if you know all that information at just one point, like where I'm standing here, then the Taylor theorem tells you, well, knowing this information, we can predict with infinite precision exactly what the value of this function is going to be right here in the vicinity of that point. Okay? So if you know the value of the function and all of its derivatives at one point, you can predict with infinite precision exactly what the function is going to be in the vicinity of that point. Take the function f of x. Okay? I only know information about f at point A. That's the point I was standing at. I know f of a, I know f prime of a, I know f double prime of a, I know everything, all the derivatives. It's an idealized situation, but we're going to make a point out of that. We're going to use that to our advantage. If we know all of these values, fa, f prime of a, etc., and we want to evaluate the function at some other value x, okay, then this formula gives you that value of f of x. It's a polynomial in x, if you think about it. So this could be exponential, sine, cosine, whatever. You know the values at one point, then you can predict the value at a neighboring point. Okay? F of a plus f prime of a times x minus a. Now notice x minus a, that's a radius around a. That's a vicinity around a, or around x. You can twist the language here. And then x minus a squared, x minus a cubed, all the way x minus a to the n. We usually say that this is the Taylor series of f of x around a or in the vicinity of a. Okay? So for example, the Taylor series of f of x equal e of x, e to the power x, in the vicinity of 0 is, you apply the formula, e to the 0 plus e to the 0 times x minus 0 plus etc. dot, 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 which gives you that polynomial that we implemented just a minute ago. Notice I have an exact equal sign here. No approximations. This is exact. This is true in the exact mathematical sense. All right. So now, let's do this, actually. Go ahead and grab a paper or your iPad or tablet. And now do the same thing for the exponential function, but in the vicinity of a equal 1. No, you have to do it by hand. This is by hand. Yeah, there's. I don't think you can do that in Python. We're trying to find a formula, a mathematical formula for ex in the vicinity of x of a equal 1. Okay, so a equal 1 in that formula. Just apply that formula. Just write a few terms in that formula, just a few terms. Keep it in polynomial form. So you're going to get like x minus 1 and x minus 1 squared, x minus 1 cubed. Just leave them as is, those terms. Remember, the derivative of e to the x is e to the x with respect to x. So f prime, f double prime, f triple prime are all e to the x. Well, no. So look at the formula. F of a, right? Not f of x. So you on the right-hand side, it's that vicinity. It's around that point 1, okay? Just simply substitute a with 1, all right?
Oh, substitute A. Wait, so in this case, am I doing this right?
No, no. You on the left-hand side, you have e to the x, right? That's e to the x at any x. Doesn't matter. But we're doing that Taylor series around the point 1. And the point 1 is going to show up on the right-hand side instead of a. No, of a equal 1. You expand a function around a point, not, yeah. Okay. F of a, or f of 1, is e to the 1. The second term is f prime of a. F prime for the exponential is still exponential e to the x. Evaluated at a, that's e to the 1. And you have x minus 1, that's x minus a. For the second derivative of e to the x is e to the x. Evaluated at a equal 1, that's e to the 1, and then x minus 1 squared, and so on. So this is what you get. This is equal to the previous one, exactly, with all the infinite terms, okay? All right, so now what happens when, what does it mean to have a Taylor series and not be able to do all of the terms? Okay, so we're going to visualize this in Python on Tuesday. Unfortunately, we don't have time to do it now. All right, well, have a good weekend. I'll see you on Tuesday, okay?